Hey darts fans, that's Timo Newman here, the transporter. Welcome to the Good Ship Undarted Waters, and this is the second video in our mini-series on philosophy and strategy of improving technique. Now, in the first video, we talked about improving in scientific terms as optimization, and I gave you a bunch of examples of how nature, both in the physical universe and in living systems, is filled, saturated, I said, with optimization. So nature does this all the time, and she does it brilliantly. So if nature's doing that, why don't we learn from nature and let her educate us in our darts how we can optimize better? And what I'm going to do in today's video is give you more of a physics kind of point of view about how we can optimize. And then in the third video in this series, we'll talk about how does biology optimize stuff, and that's going to be more about adaptation and evolution. But the key word today that we're going to remember is annealing. Annealing is going to be where we get to in hopefully 10 minutes time or so. So let me get the whiteboard and give you a brief reminder of where we left off in the first video, and then we'll take it from there. So put the old light off there. Almost got 3 bulls there. That's always a tricky one. It's a hard shot, the 3 bulls. I've not done it that many times. I will try and do it one day for one of our videos. That will be cool. So what I talked about last time was an optimization machine, and we've got to put all of this kind of stuff, the atoms of optimization, into our machine. And for a darts throw, what is that stuff? We broke it down into 4 categories: stance, action, grip, and the head and the eye placement. And we did a very, very crude analysis here. We just wrote down a bunch of things that made sense within each of these categories. And then very, very crudely, I said, well, how many different kinds of those are there? How many different orientations of your feet? How many ways to lean? How many heights of your elbow relative to your shoulder? And we just gave very conservative estimates. But the point of all that was that we easily listed 11 things, and when we worked out how many different combinations there are, it looked like 27 different stances, 90 actions, 16 grips, 9 ways for your head and your eye placement relative to your throw, and you multiply all those together, you get 350,000 different throws. And that's more than you can ever even try in a lifetime. Okay, and that's a conservative estimate. You can easily multiply that by 1,000. Okay, and it's not even including what darts equipment you're using. And there are 11 of these in the list, and that means that our optimization is happening in an 11-dimensional space with at least 1/3 of a million points, more like hundreds of millions of points. So what I tried to basically say last time was, we will never individually find our best throw. Okay, it exists in that number. One of those is our best throw. We will never find it. So we mustn't worry about what in scientific terms you would call finding the global maximum. We don't have to worry about that. Aside from that very perfect best throw for each individual, there will be hundreds of really good throws. And our job as darts players who want to improve is, how do we efficiently find really good throws rather than just good throws? Because you will naturally find a good throw feels comfortable, fairly accurate, you feel like you could improve. But the whole point of today's video is to say that's not good enough. It's too easy, and I don't mean that in a patronizing way. I mean that just like sitting in a chair is easy, finding a good throw is easy in that sense, that you'll relax into it. But that's the whole point of this annealing I'm going to talk about, is that there are ways that we can excite ourselves in the physics kind of metaphor to find much better throws. So let me get my eraser and get rid of all of this, because we've got to do 2 things today. One is, I need to kind of give you a sense of how do you represent this 11-dimensional space, and I'm just going to do that really, really quickly. And then how do you navigate it? And that's where the meat of the problem really is. Okay, So how do we represent this 11-dimensional space? Right, so you can't think in 11 dimensions. Okay, let's just agree on that. We live in a 3-dimensional space. Physicists often talk about a 4-dimensional space-time because time is like another dimension. So some physicists have trained themselves to be able to think in 4 dimensions, but 11 is too big. But what we can be sure of is that it's going to be filled. If you imagine that every point in that space you have a measure of optimization, then it's going to be filled with valleys and peaks and ridges. And here's my little model of that, which is an egg box that I've done some surgery on. So this is like a 2-dimensional space where the ridges and the peaks and the valleys are for each point in that 2-dimensional space to measure the accuracy. So that's the best accuracy right there. That's the highest one. That's a fairly good accuracy. This is much poorer here, okay, and that's a good accuracy, but really not one that you'd want to be stuck on. So this X box gives you an idea of a 2-dimensional kind of optimization problem where you've got different peaks and valleys in terms of accuracy, and how do we find these peaks? But we've got an 11-dimensional, and really it's higher dimensional because we didn't even talk about the darts, okay? So how can we kind of think about this? And the way that I want you to imagine it is, you know, if you're looking at a mountain range from a distance, even though this could be the mountain range, if you look at it from the side, can you see that the skyline there, how can I do that? How can I hold it? It's hard to hold this thing. Sorry, just bear with me here for a second. Goodness me, why can't I do this? Okay, you see that skyline there is actually what you'd see from a distance. You'd see a peak, a peak, a peak, a peak, and you can sort of draw a line like it would be like the skyline, but those peaks aren't necessarily next to each other. They might be quite far apart. But when you project it, what I'm trying to say is that you basically project it into one dimension, give you a skyline. At least you get an idea of how smooth is that mountain range. Does it have many peaks or just a few? So let's get rid of the egg box because I didn't do very well with that. So with the egg box, you've got the idea that you can look at that skyline. We can do the same with our 11-dimensional space. We can imagine that. So instead of 11 dimensions, we're going to talk about a 1-dimensional space. So we're going from 11 dimensions to 1 dimension. Okay, and this is our space compressed onto 1 dimension. And in this, I want to plot the accuracy for every point in that space. Okay, let's just move that slightly there. And it's basically just going to be filled with peaks and valleys. Okay, so it's going to look really, really complicated. So let's just look at a piece of it. Okay, these are all places. These are all good throws. Or this is a really good throw. That's like a terrible place. You would never be there because you'd be so bad. You would just move away from it very instinctively. Okay, so that's kind of a little piece of that 11-dimensional space. Now, I did actually try and make a video yesterday just talking about representing this space, and it was horrible. I actually watched it after I'd finished, and I even fell asleep. It was so boring. So I just scrapped that idea. So the point I want to try and make about this is that we can't really imagine the 11-dimensional space. But what I did get from yesterday's video when I was preparing it was I sort of estimated how many peaks might there be, and I estimated roughly 1,000 peaks. Okay, sort of like sizable peaks. So this is a tiny snapshot then. This line would go on maybe for 100 yards and there'd be hundreds and hundreds and hundreds of peaks. One of them is the highest. We're never going to find it. But if we look at a little piece of this space, we see there are places we'd rather be. You'd rather have that accuracy than this accuracy or that accuracy. So now we're getting to the chase. Now, how do we navigate a space like that? I want to just zoom in. Let's say we zoom in on this region here. So we're going to zoom in, and we've got a peak, a really nice peak, and then some peaks here. And remember, the higher up it is, the better, the more accurate. And these are all different throws. Okay, so if you're a beginner, let's say you're a beginning darts player, you throw some darts for, say, a few weeks, you really like it, it's a fantastic game, you really enjoy it, and you have settled on an action. Now, to be honest, unless you're Gary Anderson, who the legend is that he threw a 140 with his first throw, and he has a beautiful action, everyone loves Gary Anderson's action, but if you're a mortal, okay, then even though you've settled into a throw, it won't be a very good throw, and you won't be very accurate. So what you'll be sort of here somewhere. All right? Or you might be somewhere like here. So that's kind of where you've ended up in this huge space, and it's happened pretty much randomly. It's just something that felt comfortable to you. And if you then practice and practice and practice, what you're going to do is hone that throw. And let's use a different color here. That is going to make you more accurate, and you're going to slowly make your way to this peak. And that might take you a few weeks, okay? And that's what I call honing that throw. And there's nothing wrong with that. That's perfectly natural. We all do that. So you may be a couple of months into your darts journey by now, and you might start to get a bit frustrated, because what you might notice is that even though you're practicing a lot, you're not getting an awful lot better. Why aren't you getting an awful lot better? It's because you have reached a local peak. By local, I mean this peak. You know, if there was low cloud here, you wouldn't know there was a mountain next to you. So let's imagine there's just like low cloud. So all you can see is this. You think, oh, I'm on a pretty good peak here. I need to just, it's somehow going to get better if I keep practicing. No, it won't. You are stuck here. And honing is not, this is my philosophy, is not a very good way to spend your time when you're a learning player. Okay. Because that's not what works in nature. All right. So how can we bring some physics to this? Right. The way we bring physics into this is the following. We take this whiteboard, we don't throw it away after the egg carton, we turn it upside down. And why did I turn it upside down? Because if we turn it upside down, and instead of talking about accuracy in this direction, we talk about energy then this is what in physics we call an energy surface, all right? And this is a complicated energy surface, and that dart player has found themselves in what physics terms we call a metastable state. And if it's not perturbed, it will stay there forever, pretty much, okay? But you might want to be down here at what we might call a ground state, if it was the very lowest state, or a much deeper metastable state. Now, where do you see things like this in the physical world? I can give you two beautiful examples. Glass and steel. Okay, so when you make glass or when you make steel and you solidify it, it's very brittle. Why is it brittle? It's because the microstructure is not very well equilibrated, okay? And it's basically stuck, in physics terms, it's stuck in metastable states. So these metastable states, let's talk about, say, steel, these are very brittle. Why are they brittle? It's because the microstructure has not equilibrated. So if you shock that system, it can't respond, it doesn't have any resilience, and it will fracture. Same is true of glass. So over the centuries that humans have worked with glass and steel, what have they figured out? What they do is they anneal it. Okay, and what is annealing? Annealing is that you raise the temperature of it. You don't melt it, but you raise it to a very high temperature around where it's going to be, you know, glowing hot, and you leave it there, and then you really slowly cool it down. So what does that do then in the physics analogy? If you raise the temperature, you're giving it a lot of energy. You're basically taking your system that was here and you're just giving it a ton of energy, and it's just going to be zipping around. And then you slowly cool it down. It's going to be exploring that whole area because it has all that energy. It's going to be exploring the space. And you cool it down slowly. It might return to here, it might return to here, but it has lots of energy. But you're not shocking the system, you see, because you're just cooling it slowly. It will very likely find itself in here and go all the way to the bottom as it cools down, and it will end up here. That is what the annealed glass or the annealed steel has done. It's what's called ductile. You can work with it, and it's resistant to a sudden fracture. Okay, and it's a massive innovation for working with glass and steel, as we know. Okay, so we don't want to be like cast iron, which is quite brittle. We want to be like carbon steel, ductile and very resilient. Okay, so let's turn the physics picture upside down again to go back from darts. So we just go from darts to physics by turning the whiteboard upside down. Fantastic. So back we go, back to darts. What did we have to do to go to being stuck in a very mediocre throw to getting to a very good throw? We had to be prepared to explore the space. In other words, we did not hone. If we did things that made us less accurate, we didn't care. Right? So going up in temperature in the physics analogy is like being less accurate in the darts analogy, but the reason we do that is we explore. Okay? So remember, each point along this line is a different grip, a different action, different stance, different head position. So if we want to anneal, did I write the word anneal on here? No, I'm not sure I did. If we want to anneal to get to here, to be ductile, so that we are not a brittle darts player, that our action doesn't just fall apart if it's shocked, but it can respond and it can be really useful under different situations. We have to, as we learn, the annealing process is our learning process. We have to explore the space. That's my big message from the physics analogy. What does that mean in practice? And this is actually what I did. I have a pal who kept up with my darts journey, and he was astonished at the things I was doing. He couldn't believe it. And I can't say he was a big supporter of it at first, but he got on board later on. But what does it mean to explore the space? Well, here's a darts throw, right? What I was doing early on was having a very high action like that. Crazy stuff. I didn't know any better. I was only 2 months in. Why did I do that? I found it really comfortable. So I would throw like this. I would throw up and I'd do it really fast. Now, I don't do that anymore, but why did I kind of play around with that? Well, what I found was that my darts would actually land quite close together. So I got what's called grouping, and I'll make a video on grouping one day. It's a really, really important thing. But that funny action I found got me doing grouping really well. Now, what's wrong with this action is you can't aim very well. It's not good for doubles, okay? So I think I got my first 180 doing this, actually, which made me very excited, but I found it was no good for doubles. And what happened over several months is that my elbow action got much more stable in order to aim. But I think from that, I've always had a nice, healthy, high elbow when I throw. I never worry about having a lowish elbow because I was kind of learning with something up here doing this funny thing. I've also slowed down my action a lot. Okay, so that crazy elbow thing was not very accurate, but I was exploring this space and it enabled me to then find this peak. Okay, So when I honed, I wasn't honing here, I was honing here. Okay, and having a better throw, and I'm still honing, I'm still exploring, okay, and actually making this video makes me realize I need to experiment a bit more. So I'm going to sort of end there. So the bottom line of today's video is what physics teaches us about optimization in a complicated landscape like this, which you find in things like glasses and metals. You also find these kinds of landscapes in sort of hard computer problems like the traveling salesman problem that I mentioned. But annealing is the kind of the golden path to finding better solutions. So I really, really encourage you to do that. Even if you're a seasoned darts player with an action you're very comfortable with, maybe spend a couple of weeks doing goofy stuff. Change your orientation of your feet, change your back angle. If you're a straight back player, lean forward. If you lean forward, place with a straight back. Change everything, okay, and just see what happens. And you might end up going back to your old action, but it won't be quite the same. You will have somehow found a better angle on it because you have annealed yourself a bit and made yourself a tougher, more resilient, more ductile, less brittle carbon steel, which is what we want to be. We're carbon steel darts players throwing tungsten darts, all right? So let me leave it there. 3 darts at the Ockies, pals. Make them count. And I'll see you next time with What Would Biology Do? It won't be doing annealing, it's going to be doing evolution. See you later.